Hello and welcome. This is activity 8. So in this activity here, since we are not meeting in person for activity 8 due to the university requesting classes that meet Tuesday to meet virtually. So the goal this week will be for you to find this activity up on Carmen where you usually find it. If you have a stylus, just go ahead and download it and write your answers in as we kind of work on this packet here. You could do these problems on your own if you wish. You can listen to the video. You can follow along kind of here and just write your work. Just email this to your TA by this Friday at midnight. The date for that, I believe, is November 8th. So just get this to your TA by Friday, November 8th. By midnight, you'll get your points. Just show your work. That's all we want you to do is kind of try these problems, maybe listen to the solution here, and try to hopefully better understand these problems as a result. So first question here about carbonate ion. Which statement's true considering resonance in this ion? So let's think about a Lewis structure here. So we're going to have 3 oxygens connected to a central carbon. Our valence count is this here. So my valence count is 18 plus 6, that's 24 valence electrons. And so if I go lone pair for each of these, arrive at something that looks like this. Now I have a positive formal charge. The formal charge right now of carbon should have 4 electrons, only has 3. Only has these 3 electrons closest to it for a net charge of +1. The oxygens are all 7 minus 6 right now. 7 as in, let me choose a different color. So 7 as in 1, 2, 3, 4, 5, 6, 7 electrons. So think about formal charge is just trying to say, what would the charge of this be? Well, that's oxygen with 7 electrons, 7 valence electrons, so that's O minus. And so we can pull in a pair of those electrons to make a double bond. And then in doing so, we're going to change this formal charge now to be 0. 4 minus 4 is 0. And then the formal charge in this oxygen here is now 0 for 6 minus 6 equal to 0. We still have 2 oxygens that are minus formal charge that are still 7 minus 6. So we still have minus minus for 2 formal charges, the other 2 atoms 0. But now in this molecule, I can have this effect of resonance take place where I can sketch these other Lewis structures. We show these resonance arrows or just kind of showing the other structures. Probably want to show these on the side. So I have this structure here. So then I can have this Lewis structure here. You get the idea. We're just now making a double bond with the other carbon atom. And so this gets to a point where I think it's really useful for us to think that these Lewis structures that we're sketching aren't the real molecule. They're just trying to help us understand what carbonate might look like or how carbonate might behave. So in the real structure of carbonate, it's never going to be A, B, or C. It's never like you have this equilibrium taking place. So this is not what happens between these Lewis structures that we can write for carbonate ion. What happens in the real carbonate ion is that it exists as the composite of these structures, which will look something like this. So instead of having a double bond between one of the O's and carbon, that double bond works itself out to kind of coexist at all times across all 3 of those CO bonds. Now, probably not a question for the test, but in terms of a way of seeing how this bond averages out, I like to calculate the bond order just so that we can see we have 4 bonding pairs being spread across the 3 CO bonds. So we have, let me count this out here. So we have 1, 2, 3, 4 bonding pairs of electrons. That's where this 4 comes from. And then I have the actual 1, 2, and 3 bonds between the atoms. So that's where 3 is coming from. And so the idea here is that if you think of double bonds being shorter, single bonds being longer, that this bond length is probably somewhere in between the length of what you'd expect for a single bond versus a double bond. And I think more to the point, it just kind of shows you that at all times these bonds are equal in length. So carbonate should have 3 bonds that are equal in length. It's not an equilibrium trend. It's not a very fast back and forth taking place. It's at all times this electron pair spreads itself out across all of those atoms simultaneously. So the best answer to this question is that all three bonds in carbonate are equal in length, and they're not different in length. One's not shorter than the other two, and so C and D are not true statements. So this is the effect of resonance. So resonance kicks in anytime we can sketch equivalent yet different Lewis structures. The real molecule will look like the average or the composite of those Lewis structures. Question 2, what molecule below has a linear molecular geometry? So if you notice, all of these choices here have 3 atoms. So whenever a molecule has 3 atoms, the question will be, is it linear or is it some sort of a bent structure? And so this is what linear looks like, and this is what a bent bond looks like. And so you can have a bent bond a few different ways. You can have a bent bond if there's 3 total domains, two of them are bonding. So if you have 1 non-bonding domain, 2 bonding domains, and you'd have a bent structure, or you can have 4 total domains with 2 of them bonding and then 2 of them non-bonding. And so that's how we can get bent. Linear, we get linear within 2 of the domain geometries. If we have 2 total domains, that's just the linear domain. And then we also see this within trigonal pyramidal, which has 5 total domains. And then 3 of them are non-bonding, and then 2 of them are bonding. And so when we're looking at a central atom, the question is, how many total bonds are there? How many total pairs or non-bonding pairs of electrons are there? That's how we sum up the total number. That fits us into whether we're in linear domain for 2, trigonal planar for 3, tetrahedral for 4, trigonal pyramidal for 5, or octahedral for 6. These all are cases where we want to look at, let's look at, O3 in terms of a Lewis structure. So O3 has, let's count up our valence electrons. So our valence count for O3 would be 18. 3 times 6, I can do math correctly, so that's 18 valence electrons. CS2 is 4 plus 2 times 6, that's 16 valence electrons. And then N3 with a minus charge is 3 times 5 for nitrogen, and then plus 1 for the negative charge, 16 electrons. And so if I'm doing a Lewis structure for ozone, I'd have oxygen connected, all 3 connected together. I'd complete the octets of my non-central atom. I'd then count my electrons used, that's 16, the 2 electrons left over, onto the central O. And so then at this point I'm deficient of an octet, so I make a double bond. I can then resonate that over to the other side, though I don't think this is important that we necessarily consider resonance, but we can think about how this molecule is going to resonate over to here. And so these are my 2 equivalent yet different Lewis structures for ozone. So in the case of ozone, though, when I pick up and see that I have this domain here, that's going to be a pair of electrons that then cause repulsions. So I get repulsions then with these bonding pairs, kicking it into that trigonal planar molecular geometry. So my geometry here should be about trigonal planar. So this bond angle here should be about 120 degrees due to the electron pair bond pair repulsions. And actually, if we calculate this bond angle here between the O's and ozone, we predict exactly 120 if it's perfectly trigonal planar, but probably a little less than 120 because our bond pairs are a little bit longer, more stretched out. There's a little less repulsion in our bond pair than in our lone pair repulsions. So we can even predict that bond angle should be a little less than 120. But certainly ozone is not a linear molecule. So O3 is not linear. What about CS2? So for CS2, let me do this here. So I have carbon, sulfur, either side. Now, a few ways you can do this Lewis structure. One, you could relate it to CO2 because sulfur and oxygen are in the same row as each other, so this should look like CO2s. But if we just follow our Lewis structure rules, we have a 2 plus formal charge. I can reduce that down to plus by making a double bond. So I lose the electrons here. Sulfur's formal charge is now 0. And so then if I choose another double bond, I want it to be from the other sulfur. I make a double bond here, lose those electrons, so I end up with CS2. carbon's formal charge is 0, sulfur's are all 0 all the way around. And so now I have two total domains for CS2. And so if I have two domains, they're going to be opposite each other. And so that should be perfectly 180 degrees, perfectly linear for CS2. So CS2 is linear. And then what about N3 minus? Probably will be same electron count as CS2, but let's just take a quick look at N3 minus. Let me actually just do it up here. So N3 minus, I have to have the three nitrogens connected together in linear sequence. If I start as usual, just like I did CS2, start here, then I can count, that's all 16 of my electrons, none left over for the central N. Now I have a 3 plus formal charge. I can reduce that down to N double bond N, lone pair, lone pair. So this is a better Lewis structure because I've reduced the magnitudes of formal charge now to +2, -1 for the nitrogen, -2 for this nitrogen. If you're not sure where I'm getting this formal charge from, nitrogen should be surrounded by 5 electrons. It has 7, so that's a net charge of -2. And so then if I do this again, if I make a double bond like I did for ozone over to here, I get this structure here. So lose that lone pair. This is down to minus, and this is now down to plus. And then I can't do it again. I can't continue to expand the octet for nitrogen past 8 total electrons. So this is where nitrogen's happy with 8 total electrons surrounding it. And then clearly I have 2 domains. Now, if you want to argue that, well, what about this structure here? Is this a better Lewis structure? I don't think it is because you have a higher magnitude of charge. So if you go with this Lewis structure here, though, notice that you're still linear in domain. And then this would resonate over to here anyways. And so if you imagine the average, if you think this Lewis structure is so good, the one that I'm sketching right now, if you think this is so good, then it's going to resonate over to here. The average looks like this. So the N3 minus looks like 2 double bonds in our best Lewis structure, negative formal charges in the 2 outer ends, a plus formal charge in the inner. Just a quick double check for the Lewis structure. If I have a -1 formal charge, +1 for the central, -1 for the outer, that's -1 overall. You should be able to calculate the charge on the ion as minus for N3 with a minus charge overall. So we're good with 2 double bonds, but clearly this is a linear molecule, just like CS2 is. So B and C are both linear. A is bent. Question 3, based on VSEPR, what are the bond angles we expect for the bonds that are labeled 7 and 8 in this figure? This is one of the homework questions from the back of the book. But the bond angle about this carbon here has 2 domains. So I'm looking at this carbon here, I'm just saying, how many domains does it have? And the answer is 2. So it has 2 bonding domains plus 0 non-bonding domains because there's no lone pairs on that carbon atom. And so what I do is I count this is domain number 1, this is domain number 2. So a multiple bond is still just one domain, and then the single bond's another domain. So these have to be perfectly 180 degrees. And so we should expect that to be pretty dead on to 180. Now 8, this is a trick here in a way. 8 looks like 90 in the figure, but it's not really 90. This is just a Lewis structure. We have to interpret 3-dimensional shape. The way I would probably try to interpret 3-dimensional shape here is picturing a tetrahedral carbon, and then this would look something like this. So 180 degrees here, and then this bond angle here, or this bond angle here, or these, all these bond angles should be about the same. These will be about 109.5 degrees. What I'm basing this on is for 8, this carbon here is tetrahedral. So the central carbon for that bond angle is tetrahedral. Why is it tetrahedral? Because we have 4 total domains, and all 4 are bonding. So it should be 180 for 7 and 109.5 for 8. Now again, it looks 90 in the figure, but you have to think, we'll show you a lot of Lewis structures where you have to interpret the 3-dimensional shape. So whenever you see a structure that's a Lewis structure, don't automatically assume that that's the molecular geometry. You have to sort of sketch or think about what that molecular geometry is based on the total number of domains. Now, in some regard, I wouldn't mind if, and almost think it's better if they give this question CH3CN and don't even show you the structure and start talking about bond angles, so that you have to kind of put together this connectivity here. And then if you start from here, then you'd have a 2 minus and a 2 plus, so then you end up getting to the triple bond without even like being shown it exactly. So they're showing you the structure so you don't make a mistake on the Lewis structure. But the key is that if we're sketching the Lewis structure, we get to here, then we have to interpret the 3D shape from the Lewis structure about then thinking of how many total domains there are. So that's how we then go 4 domains, tetrahedral. So we sketch it something like this and then continue on for the linear carbon. Question 4, which molecule below has a trigonal pyramidal molecular geometry? So a trigonal parameter molecular geometry would have, have 3 total domains. And they all have to be bonding domains. Okay, so I can quickly rule out SF4, because SF4 makes no sense, because to have 3 total domains, I can't have 4 bonds. So I am going to have at least 4 domains about the central atom in SF4. I could do it real quick in terms of a Lewis structure. So Lewis structure, SF4, looks something like this, lone pairs around the fluorines. And so that's 32 of the electrons. SF4 has 6 plus 4 times 7. That's 34 electrons. That's 32 assigned. So we end up with 2 lone pairs on sulfur. So SF4 is going to be fitting into trigonal, bipyramidal, and it's going to look like a seesaw structure. I'll move on from that here, but this is fitting into 5 total domains, and then 4 of them are bonding. 1 is non-bonding in terms of our total domains for SF4. SF2, I should be able to rule out SF2 and CO2 as well, because they don't have the right number of bonding domains. So SF2, if I have the fluorines here, I count up my electrons, 6 for sulfur, 7 for the fluorines times 2, that's 20 total electrons. I have 16 thus assigned. So the difference of 4 electrons onto sulfur. And so now if this is my Lewis structure, this isn't 180, this is more like 109.5 degrees, because this is tetrahedral, because I have 4 total domains. So I have 4 total domains, 2 are bonding, 2 are non-bonding. Is the idea for this structure here. And then CO2, it's pretty clearly this structure here. So that's linear molecular geometry. So our choices are going to come down to ClF3 and ClO3 minus. So let's just do ClF3 first. So let's do ClF3. So 7 times 4, that's 28 valence electrons. So central chlorine, 3 fluorines attached, lone pairs on the Fs. That's 8 times 3, that's 24 electrons used. The 4 electrons left over onto the chlorine atom. And so this now has 5 total domains. 3 are bonding, 2 are non-bonding. And so for this structure here, this is going to fit into trigonal bipyramidal, not trigonal pyramidal, but this is trigonal bipyramidal, and the molecular shape here will be T-shape. So hopefully the answer is ClO3 minus, just by process of elimination so far. So for ClO3 minus, a double check it's right. 7 for chlorine, 3 times 6 plus 1 for the negative charge. That gives me a total of 26 electron. No, sorry, can't count. Yeah, I can't count. That's 26 electrons. Okay, yeah, so 26 electrons. Let me actually take a look back here. Trigonal, I thought this was a trigonal planar. Trigonal pyramidal is where we actually have 4 total domains, and then 3 of them are bonding, 1 is non-bonding. That's how we get trigonal pyramid, is going to be within the tetrahedral domain, so having 4 total domains, but only 3 of them being bonding. Okay, so I was getting confused here, had to hit pause for a minute because I was thinking ClO3 is not going to be trigonal planar, so how are any of these answers correct? But ClO3 minus is going to be the answer to this question. When we think of its structure, I put my 3 O's onto the chlorine, lone pairs around the O's like we usually do, the non-central atom octets, and so that's 24 electrons, 8 around each of the oxygens, and so it leaves 2 electrons behind, the 2 electrons placed onto chlorine, and so that's what gives chlorine the total of 3 bonding domains and then 1 non-bonding domain. And so that number of domains would match for ClO3 minus to be trigonal pyramidal in its molecular geometry shape. And so for thinking of the shape of this molecule, think central chlorine, oxygen, oxygen, oxygen. Let's do the oxygens here, and let's put a lone pair on this position there. And so that's kind of what ClO3 minus can look like, is lone pair in one of the positions of the tetrahedron, the tetrahedral structure with these O minus ions. If we calculate the formal charge on chlorine here, chlorine's formal charge should have 7 electrons surrounding it. And let me put this in a different color. So I have 1, 2, 3, 4, 5 electrons closest to chlorine. That's plus 2 formal charge on chlorine. And the O's are all 7 minus 6s for minus. And so we have these minus O's, 2 plus formal charged chlorine. Now, you might be thinking this is kind of an aside for the structure, but if we think of this Lewis structure here for a minute, just to re-sketch it, if you're wondering, should we consider multiple bonds, and does that change the answer to this question? If we do so, the answer is going to be, it won't change the answer to the question if we put a double bond here and say put a double bond here, and so we end up with a single and 2 doubles, but somehow those are going to resonate with each other so that all 3 of these bonds end up being equal in length. If we do this Lewis structure, now the formal charge of chlorine is 0. These oxygens are 0. This one's still negative. And so somehow all the O's are still going to end up with the same charge. All the bonds are going to still end up being identical to each other if we consider this structure here. And then we still have 1, 2, 3, 4 total domains. So remember, a double bond would still be a single domain, so we'd still have the same number of domains. We'd still have the same molecular geometry name and structure for the ClO3 minus ion, whether or not you have 3 single bonds between O and Cl or 2 doubles and a single. Question 5. What is the electron domain geometry and molecular geometries of BRF5? So for BRF5, I have 7 valence electrons for bromine, 7 times 5 for the fluorines. That's a total of 42 valence electrons. So I have my central bromine. I put my fluorines on, and so then I attach fluorines to 5 of the positions around bromine, lone pairs around each. You don't necessarily have to, you could just assume or imagine there's all these electrons. I don't know if you absolutely have to show this, but there's 8 electrons around each of the fluorines. There's 5 fluorines. But the key, whether showing, you got to make sure to count it correctly to get the 2 electrons that are left over that we put onto bromine. And so those are going to go onto the positions of a tetrahedron. Why tetrahedral? Well, I have 6 total domains. 5 of them are bonding. 1 is non-bonding. And so that's how I get 6 is 1 plus 5, 1 non-bonding domain. That's the electron pair, and then the 5 bonds to fluorine. And so that should be octahedral electron domain geometry. So octahedral. And then the molecular geometry name is, well, how do we name something that has this basic structure like this? And then we have like a lone pair in one of the spots of that octahedral structure. So if you notice, this is making a square pyramid. So we get a square pyramid shape that emerges from this geometry. So this should be square pyramidal. So whenever you have a molecular geometry, it really, I think, is helpful to sketch it and try to think of how are we going to name the structure left behind. So again, just think, for tetrahedral, just put a lone pair in one of the spots and then just think, well, what do we call the shape that emerges? If we have atoms in such a way that we get 2 pyramids, that's what we call a bipyramid, but here we just get a square with 1 pyramid on the top side. So we're naming just the shapes of the atoms. So when you think of the atoms here, the molecular geometry name is just kind of, well, what name do we give the shape of where the atoms are? That shape still depends on where the lone pairs are. So it still depends on the molecular geometry deriving itself off that electron domain geometry. But the name of the molecular geometry, this is just kind of like our atom geometry. So the two still go hand in hand to each other, but we're just naming where the atoms are. Okay, moving on to question 6. Consider the molecular polarities of the molecules below. What can we say about the polarities? Well, let's start with SF6. And so whenever we have a molecule like SF6, 6 valence electrons for sulfur, 6 times 7 for the fluorines. That's 48 total electrons. So we have something that looks like this, where we have an octahedral domain. I'm not going to write all the electrons around F, but each F has 8 electrons. There's 6 of them, so 6 times 8 is 48 electrons. There's none left over for the central atom. And so we have a octahedral molecular geometry and domain. And so if you imagine the tug of war that happens about these two fluorines, they cancel. These two tug of war fluorines cancel, and these cancel as well. And so our dipole moment here ends up being equal to 0 for this molecule. This molecule is perfectly nonpolar just because its individual bond dipoles cancel. So fluorine's still electronegative, so we have all these electronegative fluorines, but the net effect is that they're all opposing each other perfectly in this molecule. This is one of the reasons I mentioned in class, in lecture, you can actually breathe in SF6 in a lecture demo. I don't like doing it. It's not my preferred demo to do because it kind of, you can feel the fumes of this gas coming out as you breathe, but it makes your voice deeper if you do breathe it in, to do like a demonstration, kind of like how we breathe helium in and make our voice high pitched. But the key here is that this molecule is nonpolar. If it were polar, I think it would absolutely kill us if we breathe this in, because it would be doing all kinds of craziness with the fluorines interacting. But because the fluorines are attached in such a way that they're opposing each other, then this molecule is perfectly nonpolar. If we look at SF4, where now SF4 ends up with this molecular geometry here. Now I'm kind of going back to where I remembered it had a lone pair on top of the 4 fluorines. So if you remember having, I'll show the lone pairs on this one here just to make sure that we see that we had 34 valence electrons for this molecule, 6 plus 28, and then we're subtracting the 32 electrons around each of the fluorines to leave the 2 behind that we sketch onto the central atom. That it's important that we see that lone pair there, because that kicks us into trigonal bipyramidal molecular geometry, and then the electron, so this is the electron domain geometry, and then the molecular geometry for this one would be seesaw, because we're just trying to name, well, what would, if you take your iPad, I'm kind of taking my iPad and like flipping it on its side real quick, that you can kind of like teeter-totter this structure. That's where the seesaw name comes from. To go back to SF6 for a minute, it has octahedral domain, and then it's also octahedral molecular geometry for both, because it has all of its domains are bonding. And so in this case here, we get a polar molecule because we have a buildup in negative charge over here in the molecule that's not countered on the opposite side of the molecule where there's a lone pair. So we have a positive charge building up on sulfur that's not countered on the opposite side in our structure. If you go to PF5, now PF5 is a case where with fluorines here in the phosphorus atom, you have a stable compound that emerges that can form where we have fluorines all the way around, 5 plus 5 times 7 for 40 total electrons. So I have 8 electrons around each of the fluorines. That's all 40 electrons now left over for the central atom. So this is the case here where we have a trigonal bipyramidal molecular geometry and electron domain. So we have this for both the electron domain geometry and the molecular geometry, just like SF6 had. And then this here now has the case where our dipoles are all opposing each other in the molecule. This molecule is perfectly nonpolar as a result. So when we have a molecule like CO2 that's linear, that's nonpolar because, again, these dipoles are opposing each other. If we have a molecule like BF3, which is trigonal planar, we have a molecule like BF3, this is nonpolar as well. So it's all about, do these individual bond dipoles geometrically cancel each other out? CF4 does this as well. So if you're in the case where you have no non-bonding domains and all bonding domains, and the atoms are all exactly the same, so we're talking O here, F all the way around, F all the way around, then we have perfectly non-polar molecule. Same thing if we have trigonal bipyramidal or octahedral. Now what about PF3? So if I have PF3, the difference here is 5 plus 21 is 26 electrons. I'm now within the case where I have a lone pair, fluorine, fluorine, fluorine for trigonal pyramidal molecular geometry. So this lone pair that I get here, because I only have 24 electrons around the fluorine, so I have to have that extra lone pair on phosphorus, which is going to kick this into bond angles here of about 109.5 degrees, maybe a little less, because the lone pairs are going to repel those bond pairs closer together. But then we don't have an atom directly on top of our Lewis structure opposing those fluorines, so this molecule here should be perfectly polar. I'm saying like perfectly polar in a situation that the bonds are polar, and then they're situated in such a way that the molecule can be polar as well. SF2, I think we're going to find that this should be a polar molecule. Let's double check its Lewis structure. So its Lewis structure looks something like this. Fluorine, fluorine, lone pairs around. The count here would be 6 for sulfur plus 2 times 7 for the fluorines. That's 20 total electrons. I have 16 thus assigned, so I need 4 more on sulfur. So that's going to kick it into a geometry much like water, where these bond angles should be about 109.5 degrees or a little less than that because of our lone pair repulsions. So SF2 certainly going to be a polar molecule. So we have SF4, SF2, PF3, these are polar. So the ones that are non-polar are, do this in this color here. So here's my polar ones on this list. So 3 and 5 are polar. So the ones that are non-polar are 3 and 5. Question 7, how many double and triple bonds does this structure here have? Now there's 2 ways we can ask this. This way is the harder way because you have to figure out the Lewis structure. But once I sketch the Lewis structure, I'll point out that a lot of times we'll just show you the Lewis structure and then you have to kind of interpret it from there. So the way I would start this is go CH2 and then go to CH. So go to C with an H and then go to another carbon and then go to another carbon and then that carbon has a hydrogen. And so go to this base attachment here. And then in terms of like, how do you know where to put double or triple bonds? One way is, well, the carbon likes to have 4 bonds. So we can kind of give, these 2 carbons here can each have 4 bonds with triple. So I have 4 bonds about this carbon here. I now have 4 bonds about this carbon here. Both these carbons have 1, 2, 3, 4, 1, 2, 3, 4. So if you ever have a case, like let me show you something that might be wrong. So like if we're sketching this Lewis structure and we want to, like say I want to do this, like why would this be bad? Well, this is bad because if I look at this carbon here, I have 5 bonds around that carbon. So that's bad. So that can't work. And so we're not going to do that. If I wanted to put just like a double bond here, then I only have 3 around these carbon atoms, so that's not going to be a good idea. So what I want to do is have the triple bond here. Now, let me take another step back to say, well, let's go back to kind of this base attachment here, and then let me also then say, well, we should be able to count our electrons. So if you're saying, okay, what's another way to come up with this Lewis structure? Well, I'm just going to count my electrons. So 4 for carbon, 2 times 1 for hydrogen, plus another carbon, plus a hydrogen, plus 2 carbons, then a hydrogen. So, 1, 2, 3, 4 carbons, plus 1, 2, 3, 4 hydrogens. So that should be 16 plus 4, that's 20 total electrons that I have to distribute. So I have 20 electrons to distribute. I started with single bonds for each of them. If I just think of my formal charges here, so those are my formal charges. Like we could be throwing electrons in, but I think what the idea would be is if we just add the double bond, we kick these down to 0, then add the triple, we kick those down to 0 and 0 as well. And then we have 2, 4, 6, 8, 10. Looks like a double. So let me resketch this and start recounting. I should maybe count with a laser pointer. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have the right number of electrons shown in the structure. Okay, and so now once I have this structure here, I can then start counting, okay, I have a double bond and I have a triple bond. So how many double and triple bonds are in the structure? I have one double and one triple. And now in terms of counting other things, like this might come up in later questions, but we can start counting sigma versus pi bonds. So the sigma bonds are all the single bonds. A double bond is 1 sigma and 1 pi bond, and then a triple is 1 sigma and 2 pi. And so so I have 1, 2, 3, 4 single bonds here. So, and then I have one double and I have one triple. So I should have a total of, and I can do this with a laser pointer too, 1, 2, 3, 4, 5, 6 sigmas. So if I count the sigmas here, I get 4, 5, 6 sigma, and then I get the 1, 2, 3 pi bonds. So 3 pi bonds in the structure. And so again, so the double is 1 pi and the triple is 2 pi. And so when we start thinking of this triple bond here, we can start thinking of being a sigma plus 2 pi and this being a sigma plus a pi. So doubles have some sigma overlap, they have some pi overlap. This will probably come up again in a later question, so we'll wrap this question up here. Question 8, which the central atom of which molecule below is best described as being sp3 hybridized. So sp3 hybridization is what we have when a central atom has 4 total domains. And there can be any count where those are either all bonding or those are 2 bonding, 2 non-bonding, or 3 bonding, 1 non-bonding. So it just has to be 4 total domains. Doesn't matter how many are bonding versus non-bonding. And so when I look at CO2 can only have a maximum of 2 domains, where I mean, like it kind of comes down to this being the Lewis structure and then this having 2 domains. So that's clearly not capable of having sp3 hybridization. 2 domains is sp hybridization. And so the idea here is that carbon goes sp hybridization, leaves behind 2 p orbitals left behind to make p orbitals with the O atoms. PCl5, some of you may say, you may remember this from high school. If you do, you have a great memory. It's sp3d hybridization, but that's really kind of fictitious. It doesn't really happen, so we don't talk about that. But it's clearly not sp3 hybridization because phosphorus ends up with 5 domains. We only need 4, so that's too many domains. CCl4 is a good answer, probably the answer to the question, because carbon 4 chlorines goes tetrahedral because I have the 4 chlorines single bonded to carbon. That's good. I have 4 plus 4 times 7 electrons. That's 32 valence electrons. So I have around each of the chlorines 8 electrons. So 8, 16, 24, 32 electrons. Carbon's formal charge is 0. The chlorines are all 0, so the formal charges are all neutral. So I have 4 total domains, all of them are bonding, so it's clearly going to be sp3 hybridization. Now what does that mean? It means carbon, being in the second row of the periodic table, has access to the 2s and the 2p set of orbitals. So it takes 1, and then these 3 p orbitals hybridizes them, so it comes up with orbitals that are going to point in this direction here, in the direction of a tetrahedron. So the idea is take the orbitals of your central atom, mix them together, hybridize them so you get orbital overlap. So for describing this bond here, we could say, well, if in a different context, you could say, well, let's describe the overlap between, let me do this in this color here. So describe the overlap between the carbon atoms and chlorine. Well, carbon has sp3 orbitals, so we'd say this is sp3 overlap here to 2p overlap, or chlorines would be a 3p overlap. So this bond here would be 3p of chlorine overlapping with the sp3 of carbon. So 3p is the largest orbital of the chlorine atom, and then sp3 being the largest orbital in the hybrid orbital of carbon. BeCl2, this is going to be a linear molecule because beryllium only has 2 valence electrons, so this is our best Lewis structure of BeCl2, and then BeCl3 looking like this. So BCl3 will be an sp2 to get trigonal planar, and then sp for beryllium. So for hybridization, it's just linear is sp. So look at the central atom. What's its molecular geometry? If it's linear, it's sp. If it's trigonal planar, it's sp2. If it's tetrahedral, it's sp3. If it's trigonal planar or octahedral, we don't talk about their hybridization sets. So this is kind of what I was getting at in the last question. So the way, if we're trying to understand the bonding in CF4, so for fluorine, you could say it's sp3 hybridized as well, but you don't have to, because for fluorine, I think what you're just thinking is, well, if you're overlapping with the fluorine atom with a carbon, so picture a fluorine atom, and think, well, this extra electron here is probably just in that p orbital pointing right towards carbon. And so the way you might be thinking of fluorine is that it's a 2s2, 2p5 configuration. So you might be thinking, look, something like this for 2s, 2 electrons, and the 2p set, 1, 2, 3, 4, 5. So we have one unpaired electron. And this is going to be in the 2p orbital that's going to point right towards the carbon atom. So, but then if you're looking at carbon, you say, well, carbon has like a 2s and a 2p set of orbitals that aren't uniquely aligned in such a way to overlap with 109.5 degree bond angles. That's where we say, well, what if we just simply say, well, what if carbon takes what was these 4 orbitals that kind of point at 90 degree angles relative to each other? What if they mix together and create 4 new orbitals that point in the direction of a tetrahedron? So we get orbital number 1, orbital number 2, orbital number 3, orbital number 4. I don't know why I'm using shading to show this, but just picture that your central carbon has 1 orbital, 2 orbitals, 3 orbitals, now and 4 orbitals pointing in the direction you need them to get overlap with the fluorine atoms. And so we call this orbital here an sp3 orbital of carbon, and it's going to overlap with the 2p of fluorine. That's just the largest orbital of fluorine. That's where its lone pair is lying. So this should be sp3 2p overlap is the bond that we get between carbon and fluorine in CF4. Now 2p just doesn't quite work because you can't show 2p orbitals overlapping to make all 4 of the bonds with fluorine. So to get the 4 bonds with CF4, we have to do this hybridization set. And sp3 sp2 kind of doesn't make any sense. I might think if we had a choice of sp3, that wouldn't be too bad, because you might say this is sp3. Is that wrong to say this might be sp3? I think it's better just to think it's 2p. You don't have to hybridize it to get the overlap. But if you notice, that's not the choice. So sp3, sp2 overlap doesn't make any sense here. And then sp2, 1s overlap doesn't matter either. sp2, 1s overlap, if we had a structure like formaldehyde here, so hydrogen's biggest orbital is a 1s. So you have the 1s, and then carbon here being in a trigonal planar bond, that would be sp2. So we'd say that you'd get 1s sp2 overlap between the H and the C in something like formaldehyde. Moving on to question 10, which angle is greater based on Vesper? And so in CH4, which is tetrahedral, this bond angle here should be perfectly 109.5 degrees because it's perfectly tetrahedral. So it's tetrahedral domain. Now what about ammonia? What happens in ammonia is that we get greater lone pair repulsions that are going to press this bond angle here, which should have been about perfectly 109.5 degree bond angles in tetrahedral, and make it a little bit less than 109.5. It's truly about 107 degrees, so it's like a couple degrees off, but it's off on the low side. And so what angle is greater? The CH4 angle in CH4 is greater due to not having this issue of lone pair repulsions like ammonia has. pH3 versus BH3. So let's do BH3 first. So BH3 has hydrogens here. It only has 6 total electrons. And so let me actually draw this slightly better here just to make sure you see that these bond angles here are perfectly 120 degrees. So that's perfectly trigonal planar. And so then if you think of the bond angles in pH3, which now has 8 electrons, the difference between pH3 and BH3 is pH3 is going to kick into the pyramidal structure. So it's going to be trigonal pyramidal, where these bond angles here are closer to 109.5 degrees and even slightly less than that due to the lone pair repulsions being greater than the bond pair repulsions. So certainly the bond angles in BH3 are going to be greater than those in pH3. And then what about going back to formaldehyde? So this is our Lewis structure for formaldehyde. If you're not sure how to get this Lewis structure here, again, just attach your hydrogens to carbon. If you do a single bond first, that's okay, but you get this positive formal charge negative, which we reduce through the double bond. And so then think about how the double bond, more electrons in that bonding pair are going to push the two single bonds closer together. So the single bond repulsions are a little bit lower. And so we should have a greater bond angle. If we look at angle A versus B, the angle A here should be a little bit greater than angle B, just because we have more electrons in that double bond repelling the single bonds closer together. To be honest, I doubt they would ask this on the test. This is a pretty tricky question, but we did talk about this, or we will talk about this in lecture this week. And so our angle A should be a little bit greater. So the HCO angle should be a little bit greater than the HCH angle. And so 1 and 2 to me are a little bit more obvious. 3 is a little bit tricky to get that angle. So it should be the CH4 angle, the BH3 angle, and the HC double bond O angle. Question 11, how many total sigma and pi bonds do we have here? We were kind of talking about this on that previous example. So we're going to have sigma bonds here. So these are what the sigma bonds look like. So the sigma overlap is the overlap that's on the bond axis of these atoms. And so we get a sigma bond here, sigma bond here, sigma bond here, sigma bond here, and a sigma bond there. So in terms of the count for sigma, that's 1, 2, 3, 4, 5, 6 sigma bonds. Okay, and so then in terms of our pi bonds, now what's going on with the pi bonds is if you think of the hybridization sets here too, this might help, that these carbons here are all sp hybridization. How do I know these are all sp hybridized? Well, the way I can know that is because they're all linear. You know, like all these bonds here are perfectly 180 degrees. We're all linear. Linear geometry is sp hybridization. And so then they leave behind p orbitals that look like this, and they leave behind p orbitals that look like this. So they leave behind p orbitals that can make pi bonds. So we can make 2 different pi bonds for the triple bond here. We get no pi bonds between the next 2 carbons, so we get no special pi bonds between the next 2, but then where we have the triple bond here, we again have the p orbitals overlap for one of the pi bonds that are left over from our hybridization, and we get them left over this way. And so then the same thing happens here, leftover p orbitals, and then leftover p orbitals. Now, I don't think you necessarily have to sketch this out, but this is kind of what the bonding model is showing us in hybrid theory, is that our triple bonds are giving us 2 pi bonds each. So I'm getting, if I'm counting these up, in terms of the red, I'm getting 1, 2, 3, and then in terms of blue, 4, 5, 6. So I'm getting 6 pi bonds here. And now if I go back to the structure, if you just go back to it cleaned up, if you say we have 1, in terms of single bonds, we have 1, 2, 3 single bonds. So that's 3 sigma. And then I have 3 triples, which each are 1 sigma plus 2 pi. So that's giving me 3 more sigmas, so 6, and then 2 pi's times the 3 triple bonds, giving me 6. So a lot of different ways you can get to 6 and 6. Oh, it's here. I was thinking there wasn't a choice, and it was right in front of me the whole time. Okay, our last question for this packet kind of comes back to a question of bond length. So C2H6, so that's CH3, that's ethane, looks like this. CH2, C2H4, so 2 hydrogens on 2 adjacent carbons, goes double in terms of its bonding, and then acetylene goes triple. And so our triple bond is going to be shorter than our double, which is going to be shorter than the single. And so the longest bond is the single. And so the shortest bond is the triple. The double's in the middle. And so this is our strongest bond here too. This is more of a chapter 8 question, but this is our strongest bond among the three, and this is among the carbon-carbon bonds. This is our weakest carbon-carbon bond. Okay, so that's this activity here. Hopefully, this activity kind of replaced the feeling of being in recitation. Hopefully you all got a chance to vote, or at least those of you, we do have international students who probably can't vote, but for those of you who are allowed to vote, hopefully you participated in the process, and if you didn't, I hope you do so the next chance you get to vote, and I will see you guys in class this week.